get some of your library stuff?
Not yet.
You just watch the video. Yeah, all the lectures are recorded. Just go on to Teams or Discord. Teams, go into the vetted one, the link will be there, and if not, go to the Discord server, and then go to the 1250 class, and that link will be there as well. The link sends you directly to a playlist, and you're all there. Especially the class I saw I was watching one today, and I can books I've recorded for myself, but some people obviously need some extra help too, so I put them up better than good as my own part. No, just scroll down. You see the name? It's right there. Keep going.
All right, we're gonna get started.
Okay.
So let's see who's here first. My last class of the day. Print is here. Shintan. Carl is here. Winston is here. Walter. Here. Omar.
Did you see me?
Arshdeep is here.
Watching
Stephen
video.
is here. Darius. Joe John.
Rewatch it.
Simranjit.
Oh, everything.
Simranjit. Rex is here. Kill it. Jasine. Kritika is here. Rosine is here. Jin Yuan is here. King Joey is here. So that makes it 13 and a visitor. Oh, 2 visitors. 4, 7.
You might have one more visitor joining later.
Yeah. 4, 7, 8, 9, 10, 11, 14. Okay. 3, 4, 7, 8, 9, 10, 11, 14. I missed someone. Oh. Was the one on the back there beside Om? Who is that? Kritika. No. Why? So why do I have one missing? Oh, you're not from this class? Or you are? You are. Yeah, you just called me. The math doesn't work, guys. Okay, again. 3, 4, 7, 8, 9, 13, 14. Oh, because Om is not in this class, yeah. I wasn't counting Om. Yeah, okay. All right. See, so that would be the ideal for any instructor, have that level of enthusiasm in a student, like showing up for your 2 sections. Can you imagine? I know it's not possible.
Wait,
It's
do
so
you,
encouraging.
do you have the section like just before this?
No, but I'm saying that he shows up for every class in this section and the other section as well.
But would you have a time turner or something? You just like travel back in time and then you're able to go to them all, or?
He does review stuff.
Hey, if you like it.
Okay, are there any questions up to this point? Today we're jumping into a new topic. So libraries should be completed because I'm releasing the assignment before the end of the week. The assignment that includes the library.
My question was actually about the libraries.
Mm.
So once we have the basic one set up, obviously I was watching through some of the videos.
we can put whatever functions we feel are important to us in that library?
Yeah, for sure. Just make my only advice is just to keep it consistent. For example, if you have your blocking delay libraries that I wouldn't put those in the GPIO, for example, because to me it seems like it doesn't belong there.
I
So you should.
It should be like a
create
separate.
utilities or something like that.
Oh, okay.
And there's nothing wrong with putting it there. It's just that the whole point of creating libraries is to put in the library prototypes and functions that belong to the same topic, right? So if we start mixing up things, then we're kind of defeating the purpose.
If I have GPIO with like a blinky light function that
But
doesn't.
syntax-wise, the compiler will be totally okay with you doing that.
Okay,
It's just more like a architecture thing. Okay. Yeah. So libraries, like I said, should be completed, and I don't know if it was this section or the other one, but I almost like showed you like all the libraries.
Yeah, it was us.
Yeah.
Yeah.
So I mean, what else can I do? I don't think I can do much more.
You could write it for us. I think that's the only other thing.
Yeah, and that would be too much.
Yeah.
For sure. Okay, so the lectures are being recorded thanks to Rex. So there's a link to our YouTube channel, Rex's channel, with all the lectures recorded. So if you're behind, all you have to do is just catch up. But what is a bad idea is not showing up for class and to not catching up, because discourse ramps up like very quickly. Okay.
It's all on a playlist, so
Yeah.
start from the first one and work your way down.
Okay. Let's just go here. So today we're going to talk about the UART or UART. The explanation is it's down below in the lesson, but UART stands for Universal Asynchronous Receiver Transmitter. Okay, and USART is the same thing, but aside from being asynchronous, can also be synchronous. Now, does that ring a bell? Like what synchronous could mean? My guys that I had on in 1550 last time, does it ring a bell? The word synchronous.
Yes.
What does it ring? What does it relate to?
Synchronous could mean if we had data in one register and we were to have this as, synchronous, that means that we would have essentially like a copy and paste for that same data, where it would just kind of flow down into the next memory
Okay,
address.
but what component does make something synchronous? Lock. Excellent. So these means lock. That's a great answer. Yeah. Okay. So where do I start with this? Now, UART refers to serializing data. Okay. So if we go back to our 1550, let's pretend that I have an 8-bit register here. Right? And then I have another 8-bit register here. Forgive me for my terrible drawing skills. Then do I have a red? Yeah. So let's say I want to copy, and we're going to just do like an 8-bit register because obviously that simplifies the understanding. If I were to copy like this, having lines like the red arrows that are marking, is that serial or parallel? Is it serial? We only took 1550 last term. Yeah, so I wouldn't blame the ones that are taking this for the second time. No? It's parallel.
Yeah.
Why? Because you have as many lines as bits or pins, whatever you want to call it, right? So this will be my bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. By the way, now that I write these bits is everything in this course. Bitwise operators, masks, bit shifting, bitwise or, and, complement, all that you should master. If you don't understand how that works, I hate to say it, but you do have a problem. And you need to fix it as soon as possible. Because everything that will come after in this course and the following one will be about that. So we need to really understand what a mask is, how we mask, how we know if a bit is 1 or 0, how the bit shifts and all that. And we've been practicing quite a lot. But I can provide some extra help maybe, in case you're wondering. But if you don't approach to me, I will just assume that everything is clear. Okay? So this is parallel. So if I wanted to do serial, how would I transmit from the register on the top to the one on the bottom? Well, I'll sort of have to start doing this, like bit shifting or the other way around, but somehow the bits will have to go one by one. So that would be serial, okay? So it's very important that we do understand the difference between serial and parallel. Now, any reason for doing serial over parallel? Or parallel over serial?
Parallel is faster.
Parallel is faster. Okay. What is the disadvantage of parallel?
For parallel transfers, it's always parroting or parodying, or to parody the data. So
what if I have a 32-bit register? How many lines do I need?
32.
If I have a 64, 128. So what happens in terms of cost? So if we think that now manufacturing something, obviously it's costly. In fact, if you were to connect whatever device to the computer, if the super popular USB, which stands for what? What does
Universal serial.
Universal
bus.
serial bus. It's serial as well. See? Now, why is it so popular? Well, because it's serial, you need a cable. Can you imagine 64 bits? You will need a cable like this, right? You have 64 lines going. It will be super fast, but inefficient, right? Probably not quite. So that's why serial is so popular, okay? Because in terms of cost, it's cost effective, so it simplifies things. Less wires, less hardware. Now, parallel also has a little bit of a disadvantage, but that goes beyond the scope of this course. When you take 2750, you will learn a little bit of PCB design. You also learn a little bit in 2150 later. When we have things communicated in parallel, like if I had a parallel memory, so the bits start traveling through this line, and then through this line, and then through this line. And there's a question of electric currents, because at the end of the day, the bits are highs and lows, and that's electricity flowing through the wires. So what if the wires are not all the same length?
Then you start to get into impedance issues or difference in impedances.
Yeah, and basically, if you think about the bits traveling through the wire, if the wires are not the same length, some bits will arrive before others.
So you
if
corrupt your data.
Pushing data like crazy, you obviously have problems with corruption of data, right? Because of that. So it's quite a bit of, it's got a couple of disadvantages to do parallel, okay? So in serial, that's what we're going to study. So the objective of this lesson is that you guys understand what the UART protocol is and how does it work, what's the frame structure, how we can configure, well, I don't know if we're gonna get that far, but we have 2 hours, I think we will. How we configure the STM32 UART or USART peripheral. In fact, the USART, we're going to use a USART, but for the purpose of this course, we're always going to use it as UART, so no clock signal. Okay. We're gonna learn how to program it using the register level. So we're gonna go into the registers and program just like we've been doing our GPIO and all that. And we're going to build eventually a minimal UART library. So we keep building libraries for our development. And we're going to transmit and receive data using polling. Okay? I'll explain later what the difference is between polling and influence. So again, UART is Universal Asynchronous Receiver Transmitter. It's a serial communication protocol that transmits data 1 bit at a time over a single wire. Okay? It's asynchronous, meaning no shared clock. So excellent answer by Carl. Both devices must agree on timing. Okay. If we don't have a clock signal, and this guy is transmitted at speed 100, and this one is receiving at speed 50 or whatever, so then we do have a problem, right? Now, when we do have a clock signal, then the one that handles the clock can dictate the pace, right? Just like when you're doing your flip-flops and you set the clock edge, you're dictating the pace of how things are being latched in. In this case, it's very important that the two devices have the same speed, and that is what's known as the baud rate, which means bits per second. We will discuss that more. So to have a simple UART or serial communication, we need two devices, okay? Can anybody guess what those devices are going to be? Device 1 or device 8? What are we going to use? What material do you guys have for this course? What have you purchased?
Some boards.
The board. So the board itself, or the micro, is going to be one device. Anybody guess what the other device can be?
Another micro.
Excellent, another micro. Actually,
Or
I ordered the...
a 7-segment display could also
Well,
be.
the 7-segment display didn't order, but I think I do have enough. I hope. I forgot to. This one is zero, is yours. This 7-segment display. And I said that this, together with this, is about $5. So I think I received these ones today at home. So I'm gonna bring them maybe next class. And I'm gonna collect these ones. Hopefully I have enough. Otherwise I have to order a few more. And hopefully they arrive soon. But anyways, yeah. Could be a display, could be another device, so it would be a good activity to actually communicate two words. What other device could be?
An infinite amount of answers.
Yeah. But think about the devices we have here in the lab or at home.
Maybe 82.
82? Yeah. There's a possibility actually to connect the UART pins to the 82 and see the data. Yeah, that's a great answer. But somebody has forgotten the most obvious one. Oh, all of you have forgotten.
Computer.
The computer, yeah. The computer definitely has a serial port that you can use to communicate. So the first approach that we're going to do is communicate our board with the computer. What do you think we're going to use on the computer to transmit? And what are we going to transmit? Can anybody guess? What could we transmit? Huh? Data?
Ones and zeros, man.
Ones and zeros, but ultimately, how are you going to verify that?
Oh, we have to check.
If you wanted to establish a simple communication with two devices, what would the first thing you will send? What would be the first thing? Or what would you think about sending?
A test communication.
Test, yeah, such as what?
it could be a number value represented in
Number,
binary,
okay.
and then on the other device, we could be
Your
checking to
spectrum is
see
the same?
if there was like the correct checksum or.
What if you wanted to transmit like multiple bytes? How can you make sense of all that?
be reading
There's
if-
something
If the pin gets,
you guys used in 1550 last term. What is this?
ASCII,
ASCII table. So it seems like transmitting ASCII makes sense because if I know how to transmit an A from the micro, I can see it on the computer. Now, what am I going to use to see it on the computer? What kind of application? Any guesses? I don't know.
Sager,
No, because Sager is to communicate with the micro. We need to do a little bit of history here.
a terminal,
A terminal, excellent. These computers, in case you haven't seen, they have these cables. This cable is not a VGA cable, okay? Although it looks like one, but some of you don't even know the VGA, right? But it did exist for video. This one actually has less pin, and it's a DB9 connector, whereas the VGA has, I think, 15 at least. It's Ultra VGA has more pins. But this one is actually what's called an RS-232 cable, which is actually a protocol that is meant to build on top of UART for longer distances. Because UART is TTL CMOS levels, meaning 3 volts, 5 volts, so it cannot really go longer distances, but this cable can. Now the computers no longer have, or no longer come with this port. In fact, these desktop computers are one of the few that remain having this port. Okay, so till probably maybe 5-10 years ago, they still build motherboards with that port, and yeah, you could expose this port through a ribbon cable, right? Because it was on the motherboard, and then bring it out through a bracket, and then you will on the back have this thing, the DB9.
so it's an RS-32 cable?
RS-232. Yeah.
232.
But we're not going to use this because we're using a modern board. The ones that were using the old board still had this thing. And
Serial over USB.
yeah, so laptops used to come also with this port, not anymore, right? Everything is USB now. Now, how do you identify the serial ports on the computer? That's something very important. Right click in here and go Device Manager.
Serial I/O.
I know I don't have admin rights. And you look for the COM ports, as in communication ports. It says COM and LPT. This is an ancient thing from Windows, because LPT used to be the parallel ports used for printers, like those dot matrix and old stuff. And the COM ports are here. Okay? So in fact, when I disconnect this board, there's one that goes away. And when I connect it back, it comes back. And it's called what? J-Link CDC UART port. See? UARTs. Communication. COM59. Okay? That has nothing to do with the other J-Link driver that I see here. That is the one that is used for the debugger. Whereas this one is a virtual serial port. So it's emulating an RS-232 like if you were using this cable, but you're just doing it over USB, which is very convenient. So that's what I'm saying. We're using a modern board. Yeah.
Mine says COM5.
Oh yeah. So in your computer will say whatever COM. It's whatever address the computer can issue to the device. Okay? All right. So now we know we're going to communicate through this port. And then what application are we going to use? A terminal. Like which one?
Well, in Linux, it would just literally be a terminal.
And you open the COM port, yeah.
But
Because Linux is
in,
everything is built in.
In
right?
Windows, it'll have to be a command prompt.
Yeah, the command prompt, I don't think you can open a COM port actually.
You can with Linux subsystem for Windows.
Oh, for the with the WSL.
Or, sorry, they call it Windows subsystem for Linux,
yeah,
which doesn't
yeah,
make sense.
WSL, yeah. Yeah, but in here I cannot say open COM, whatever, that doesn't work. So what application am I going to use?
PowerShell?
PowerShell doesn't either.
Hmm.
Here's the thing, and this probably the only one who's going to get a little bit what I'm saying is gonna be Rex. I don't wanna call you old, but.
I'm old, man, it's cool.
Windows used to come with this thing. Something called hyperterminal. Does it ring a bell?
Oh, man.
It's very old.
It's, yeah, Windows 98, man.
Yeah, I think it was up to Windows 98 or 95.
Yeah.
So that was a little terminal for communication through COM ports and serial, which is serial, or SSH, right? Telnet, all those old protocols. So they retired this. Although it's funny, in 2700, which is a 4-term course, they have an installer, well, an executable of this, and they use it, which is very, I don't understand why.
They run a compatibility layer, or they just pop up a...
Maybe some sort of vintage stuff. I don't know why they keep that, because they could use more modern applications like TerraTerm. That is one of them.
Build your own?
You can build your own in C# for sure. It's very easy from the C# Windows application opening a COM port. Yeah, TerraTerm is one. I'm going to provide a few links to these installers later. The other one is the super popular Putty. This one is very popular. Okay? And this one can also do SSH serial. And the serial is the one that you want to do, and you write the COM number here. In TerraTerm, you have to set up your port here. See, COM59, which is our J-Link, is the one that should connect, right? Sorry, yeah, that's it, correct. And then this is the speed or baud rate. So we're going to talk about this later when we actually build a program that can communicate. But what I'm saying is that if you do this and you open a connection in this COM port, which is the proper one, right, is it? So you need to look at your computer and see your J-Link, which COM number is. In my case, it's 59. So once you connect to this one and you type, well, by the way, this terminal doesn't have enabled the local echo, so I don't know what I'm typing. Now I am. If you type hello world and you send it, you actually send it through this cable to the micro. Is the micro receiving anything?
We don't know yet.
How can I know if it's receiving anything or not? How can I make it receive anything?
You could hook this up to an oscilloscope and see what's going on.
Yeah, I could see the bits coming, but obviously if I don't have code, all that hello world got lost somewhere in here, right? Because I don't have code to receive it. And that's what we're gonna do, okay? So that's the ultimate goal, okay? We're gonna send messages from here, we're gonna receive it in the micro, and unfortunately the micro doesn't have an LCD display where I can show that, but maybe the micro can send back the same thing, right? Just to start some sort of testing.
Oh, like
okay?
an echo.
Yeah. All right, so let's take a look a little bit at how the instructor works. So you may think that transmitting a character, which is 8 bits or 7 bits, depending. How many characters is the ASCII table? The traditional ASCII. You can look at this, or something online.
100 and something.
128, which is from 0 to 127. What is the ASCII code for the carriage return, the enter key? Does anybody know?
I know space is 38.
No, I put is it? I didn't have that one memorized. Let's see. No, 38 is the ampersand.
Oh,
Space is 32.
oh.
Carriage return
I have it fully memorized.
is 13. A little bit of history. Do we know where the carriage return comes from? Well, what do you do always in C# when you want to send a new line?
Enter.
/n.
/n. Carl is very bright today. Yeah, this one is actually 10, I believe.
/n.
Yeah, it's called the line fit, LF. And it's 10. This one is 13 and it's actually \r. Okay? So, and do you know where the carriage return comes from? From the typewriters. Yeah, that
Shing.
thing that, yeah, that's old. Very old stuff. Too vintage for the majority of these ones. Anyways. Okay, so we are transmitting, basically if we transmit text, characters that are printable, because some characters are non-printable. So when you press enter key on the keyboard and the terminal sends a 13 to the micro, or if you press, well, you cannot really press this one, there's no key for the line feed, right? But some characters are basically non-printable. So when you press the enter key, the micro doesn't receive a letter, it just receives as 13 and it doesn't know what that is. If it's something printable, it will receive the number still, the ASCII code, but it will be a letter that you can interpret. And those letters and printable characters are within the range of 0 to 127 and then 128 and all the way up to 255 is what we know as the extended ASCII, right? And those weird characters that you, I think you also, oh no, here you only have the lower part. Anyways, those will go here in the data bits. But the packet, the frame for a UART frame structure starts with a start bit. That is always 0. And it also has a stop bit that is high at the end. So it will have at least 10 bits. Okay? Now it can also include a parity bit, which is optional. And the parity bit is just for data integrity, right? And again, the ones that took 1550 last term, I'm pretty sure you got this very clear. Right? What the parity bit is? You just count the ones, and if it's even, you add a 1. Sorry, odd, you add a 1. If it's even, you add a 0. So that's your parity bit just to check the data integrity. Now, when we open TerraTerm, and we go to the settings of the serial port, you can see here these settings, right? The parity is here. It says none, meaning that no parity. And that is the default. We're actually not going to use the parity bit. For simplicity, we're only going to use the start bit and 8 bit. Sorry, start bit, end bit data is going to be 8 bits. So simple. 10 bits per character, okay, in total. All right. So here's an example of the frame. Start bit, it sends the least significant bit first, okay? And then at the end, stop. And the baud rate refers to the bits per second, okay? Now, when we say 9600 baud rate, it means 9600 bits per second. So when I ask how many bytes per second is that, it's not dividing this by 8 because it depends on this. It's at least 10. And if we're using a parity bit, then it's 11, right? So it varies. So we have to keep that in mind.
Oh, good old Windows, right on.
Oh, why? And updates?
Because Microsoft.
Beautiful. Any questions up to this one? You know, or maybe somebody decided to push it.
So for like it was like 9600 or 9800, I think. I mean, that's a fairly low resolution in terms of baud rate.
9600, yeah.
9600.
Yeah.
So is that just like because we're starting and we just want to see
No,
the...
it's actually a very common. There are two baud rates that are the most common, I would say. One is the 9600, and that is the default speed, like the lowest speed. There's it's lower than this, but this is the typical minimum speed.
Because in sound engineering, we like to use things like, 128 kilobit sort of thing. Like
Yeah,
it gets
yeah.
really
Now, in this case, it's serial communication. We can do faster, but 115 to 100 is a very typical one too. Although we can go a bit faster. Now this one, when you do the math, it transmits approximately 1 byte per millisecond. So it takes 1 millisecond to send 1 byte. Whereas in this one, it takes about 87 microseconds. This one is really fast. Okay? So I need to log in again. All right. How are we going to configure this UART peripheral in the micro? what is the only peripheral that we have studied so far in the micro? Can anybody tell me? What? The code that we've written, what is it targeting? What are we changing? What are we configuring? Huh? Port? But what is that port called? What is the name? Give me an example. GPIO. GPIO A, GPIO B. So the GPIO is a peripheral that stands for general purpose input output. It's the most simple peripheral you can have in a microcontroller. That's why we started with that one. We also have a UART. We have timers. We have some more peripherals that we're going to keep studying. Okay? How we configure this peripheral? So when we use a GPIO, we sort of like configure the pin as an input or as an output, right? Let me open this again. And what do we do to configure that? What do we need to change? What is the register that, well, I said the word. What do we change to configure the GPIO pin as an output? Huh?
ODR.
The ODR is to actually drive a pin high or low.
Oh yeah.
The motor, right? And what are the motor and the ODR? What are they called?
A register?
A register. Excellent. So,
That's your control panel.
this course is all about bits, bitwise operations, but it's also all about registers. So if we don't understand what is a register, we also have a problem. So we need to process this part, okay? Now, I like to categorize these registers. Here's the thing. Remember that we said that everything has an address? So particularly every peripheral inside the micro has an address, okay? And the key of embedded systems is that the interaction with these peripherals is done by the software as well as the hardware, okay? In the most simple peripheral that we have, which is the GPIO, the hardware, how does it interact with the GPIO? Button press, or something like that, right? Then that button press drives a bit high, and then the software can read that bit by doing the bit masking, right? Whereas if the software wants to interact with the GPIO, we'll use a bitwise operator in C to set that bit high and then turn on an LED, okay? In this case, the UART is serial communication. So the software could actually send something to the UART, and that should arrive on the terminal that I just opened earlier, right? Whereas if the terminal sends something, that will play the role of the hardware. It will travel through the cable and arrive at the UART peripheral. And that's how the interaction is going to happen. Okay. And embedded systems is all about configuring these peripherals to make them work. So before you can use GPIO, you have to configure it as an output, as an input, and then you can use it. The UART, you have to configure it. You have to configure the baud rate, you have to configure everything, and then you can make it work. So how do you configure? By writing into these registers, okay? And that's why I like to categorize these ones in a group that I like to call first control registers. And those are the ones that you use only once at the beginning where you configure your peripheral. So in your GPIO, an example of this is your ODR, your motor. Because in the motor, you configure it as an input or as an output, and then you just use it, okay? Then I like to say that we also have status registers. Now, this is a bit hard to understand just with the GPIO, to be honest, but I'm gonna ask for a little bit of a vote of trust. The status registers contain what we call flags. And these flags are basically ones and zeros. So within the status registers, it's going to be a bit that becomes a 1 or a 0. And that is the way the hardware communicates with the software. So it tells the software, hey, there's something going on here. So, thinking about the UART, we're going to configure it here, somewhere in the control registers for the UART. Then we're going to let it go, sit there. A character is going to arrive, then the status register of the UART is going to raise a flag and tell us, hey, I received a character. That's how we're going to communicate. And lastly, we're going to be using some data register. And the data register is very self-explanatory. It's a register where we're going to write the data to be sent out, or another register that we're going to receive the data coming and process. Okay? So these are kind of the three major group of registers that we're always going to have. So it's very common to see in the peripherals CR1, CR2, as in control register 1, control register 2. That is where you configure your peripheral. It's very common to see an SR1 or SR2 as in status register 1, status register 2, where you're going to read what's going on with the peripheral. And the peripheral that transmits data is going to have a data register as well. Okay? How are we doing with that? Okay. So, those registers are here. The BRR, for example, is the one that we write to configure the speed of the UART. Okay? The baud rate that gets calculated by this formula. But I'm going to revisit that formula in a moment. So, according to what I just explained, would you consider this a control status or data register, the BRR? Data? Do I write the data here and get sent out?
You control the baud rate with
It's a
that
control
configuration.
because I configure the peripheral here, and I do it only once at the beginning. Okay? Even though this one is not called control, baud rate, whatever, but it is a control register because it's where I configure the peripheral. See, I also have control register 1, control register 3. So many different ones. This is to enable the transmitter, the receiver, for example. Can anybody identify from this list the data registers? TDR and RDR. See? Very self-explanatory. In this TDR, are you going to write or are you going to read from? Are you going to write to or read from? Write. So in here, in this register, you're going to write what you want to send out. If you want to send something from the micro, you're going to write the data here. If you're going to receive something coming from the terminal, for example, to the micro, you're going to receive it here. Okay? And can anybody tell me or guess in which register are you going to check if you received a character or not? This one, excellent. See how this makes sense? This is how the peripheral communicates with the software. So the software needs to read the status register to know if there's something going on. Okay? Questions? ORQR is just for clearing some flags. That's a bit more advanced. So we'll leave that one for the end. Maybe next class. Yeah, I want to keep, in case you haven't noticed, when I discussed the GPIO, there were many registers, and I only used the motor, the IDR, and the ODR, right? All the other ones are for more advanced stuff that we're trying to explain now the bare minimum. Now, what you should do, you should be curious enough to read the reference manual and try to understand what the other ones do. Okay? Because you gotta practice a little bit on your own. You cannot expect me to give you all the information. Okay? I don't know if I ever mentioned this, but in the past, and with this, I promise we'll go for a break, 2 more minutes. I always, I'm very interested in the feedback I get from the students because that's how I improve later. And then after the second iteration, whatever. And one student complained that the information in this course, well, not particularly this one, but an embedded system course that I was teaching, all the information was so scattered, right, all over the place. And I found it interesting, but I felt like replying and saying, welcome to the world of embedded systems. Because that's the way it is. Because it's right, all the information is all over the place, but you cannot have all the information in one place. Because if you're working with a development board, you need the schematics for the development board, right? To see where things are connected, schematic. Then if you need to program something, you need to go to the reference manual. Then if you need some more specific information, you need to go to the data sheet. Or then some other site or whatever. So you're jumping back and forth. So being very honest, I find it really hard to do embedded systems on a single laptop and without a mouse. Because so much going on.
You need multiple displays.
You can do it, but you're slowing down yourself. I gotta be very honest. Yeah, even these computers here, they should be at least dual monitor for this course. Because you always have, in my setup at home, I have 3 monitors.
I was gonna say.
I don't think I can work with less than 2. Schematic on one side, reference manual on the other side. Code editor, see? There you guys have 3 screens. You got Sager here, reference manual, schematics. And that's the way it is. I don't see it being different. Now, if you're proficient like doing alt-tab and jumping back and forth, maybe. Let's go for a break. And we'll recap after. At 8. By the end of this. Yes. So before I start doing anything, I guess the first thing I gotta do, not in the code, but in my thinking, is to figure out the baud rate. Okay? And the baud rate for this micro is easy to calculate. It's as simple as just doing the core clock divided by the baud rate that I want, and that goes into this register. Now, does anybody remember what is the default speed for this micro? 16 megahertz. Yeah, so we haven't yet touched the clock. That's the next topic coming after UART. So then we will be able to configure the micro at different speeds. But for right now, it's just 16 megahertz. So technically, you could just hard code a 16 million here, and that will work. Okay? But I would like you to use this variable, and I will explain in just a moment what it is. Okay? In fact, I can explain right now. So I have a few things configured here. I'm going to delete everything. I'm just going to leave the delay functions that we created because we may need them. Okay? And I'm going to do this. Before I jump into the infinite loop, I'm going to say printf, which goes to my debugging console, right? And I'm going to say clock speed. And then I'm going to say percentage U, as in unsigned, okay? And then hertz. So I'm going to display the clock speed in hertz. And then close it here, comma. And I'm going to use this system core clock. See, this variable is defined here. Oh, it doesn't recognize. Why it doesn't recognize printf? Can anybody guess? Huh? Yeah, not including stdio, the standard input output library, right? So include stdio.h. Okay. So I should see this message somewhere here. Let me just run this thing. Remember, the printf goes to the debug console. It only works when I'm debugging. Oh, it looks like my micro is running at 16 million hertz or 16 megahertz, right? Now the question is, where is this system core clock variable coming from? How would you check if I ask you?
Sorry, still getting the app set up.
Well, you can go to definition, right? Right click. And it's defined in this system underscore whatever. And where is this defined? I can just in File Explorer, see it, and it's inside this package that the Sega Embedded Studio creates by default. Okay? And you can see the definition here, and by default it's 60 megahertz. Okay? But this can also get updated. But who defined all these functions? All these functions are part of the CMSIS core, which I don't want to explain so much yet because it's too early in the course. But these things are basically behind the scenes available for us. That's all I want to say. Okay? So we can use this variable always to check what is the system core clock. And then when we change the clock later, we can also call a function that updates that variable. Okay? So I know that my system core clock is 60 megahertz, and I can use this one to actually calculate the baud rate, the number that needs to go in there. That's why I'm using system core clock. Okay? And why is that important? Because if later on we run this micro at 40 megahertz, you don't have to recalculate the baud rate. You just use the system core clock, and it's going to work out. I'm going to do the calculation, and let's say I want to work at a 9600 baud rate, so I'm going to do 60 million divided by 9600. It gives me 1666.6. What do you think is going to be written into the register?
1667.
1667. Well, that is what should be written. Can I write 1666.6? No. If I look at any register, this one for example, if I hover, what type does it have? Can anybody tell me? UART 32_T. So I cannot really write a float. Okay? And if I write a float, is it going to be typecasted automatically into UART? I don't know. That could be this catastrophic if I don't take that into account. I did explain this to the other section. We've studied ints and assigned ints, and if we think about a very small number, 8-bit, I always like to do the 8 bits because that one is simple. If this number has a 1 here, what does it mean? If it's just an int type or whatever, char.
It would be that integer value.
Yeah, but there's something, if the number is signed, the 1 on the most significant bit will tell us if it's negative, right? And that's how the Deuce complement math is done and all that stuff that we studied in 1550. A little. Now, have you ever wondered how a float is represented in bits, ones and zeros?
Not until right this second.
Yeah. So that's quite interesting, and that goes beyond the scope of this course. It's probably will be studied in some computer science or whatever. Okay? But in very simple terms, the way you represent a float, if it's 32 bits, the float will have a part that is what is called a mantix or something like that, which is sort of like the base, and then the exponent will be here, and will be 2 to the power of whatever number you have here. So it's a very complicated way of representing. So if you were to dump all the ones and zeros because at the end of the day, this will be a bunch of ones and zeros, right? Representing something. If you were to dump all this into an unsigned int, you may end up with whatever weird number, like 35 million whatever, right? Because the ones and the zeros as a float are going to represent something else in Deuce complement.
Are these, do we have like a specific portion of the memory stack in which floats just kind of live as opposed to the other values, or does
No,
already
they
just
go
kind
into the
of
same memory, because at
it
the end
just
of the
handles
day,
it
these
differently.
32-bit registers will contain ones and zeros, and depending on how we declare it, is how it's being interpreted.
Okay,
right?
so it'll state
Which
like
is why it's tricky when you just dump an int into a float. It's not a problem because that's what's called an implicit typecast. Okay, but the other way around, you need to do an explicit Otherwise, you may end up in problems. Okay? And why am I saying all this? Well, because let's say I want to have, I'm not going to target the registers of the UART yet. I'm just going to define a variable here called VRR, like that, okay? Just to talk about that bar rate. And I'm going to do exactly what there says. System core clock, and then I'm going to divide by 9600. Okay? So, first question. Is this result going to be a float or not? Huh? Yes or no? No? Does anybody think yes? Why not? Well, the condition for a division or any result to be float is that at least one of the operands needs to be float. This guy is a uint 32. This one is an int. Well, unless I do something like this. I add an f, or I do something like this. Right? That's now a double. Or if I put an f, it's a float. Okay? So if I do it like this, it's going to be an integer division. Therefore, what number am I going to put there? 1666 or 1667?
1666.
Yeah, so let's verify it. Why not? We can do that. That's why we got the beautiful debugger. I just need to add the expression here, VRR. And then press F10. And VRR, we can show it in decimal, happens to be 1666. So, that might be irrelevant. Because when it comes to UART communication, there's a tolerance that at least 2%. So anything below 2% error will be fine and the serial communication will still work. And so if we have a difference between 1666 and 1667, it's actually a very minor difference. It's about 0.06%.